So the Bohr model of the atom, it's a planetary kind of representation where you have the nucleus, which contains the protons and the neutrons, and then you're going to have the electrons somewhere orbiting around the positive nucleus, which contains the protons. Okay? So this here is not a semicircle. It should be going all the way around, but just to simplify everything, I am representing that as a semicircle, but you should know that this should go all the way around the nucleus. Now, the spaces that you have right here, they represent a specific thing. That's one, that's another one, and then a third one right here. So I'm going to put that as an N3, N2, and this one here is an N1. N1, N2, and N3 are energy levels. Okay? So what we're trying to do, we have something very general. Okay? The model of the atom with a positive nucleus containing the protons and then the electrons somewhere around. So we're going from this that is very general to something very specific. Where are the electrons? Okay? That's what we're trying to do. So the electrons are located in different energy levels, but in orbitals. So we're going to have orbitals in that first energy level, orbitals in the second one, orbitals in the third one. And in those orbitals, we can find electrons. The orbitals are a volume in space. It's not just that the electron is exactly here, or here, or here. It's a volume of space where we can find the electron with a high probability. That's what an orbital is. Now, the orbitals are described by a set of numbers, and those numbers are quantum numbers. They come from the solution of a very complicated equation, and we can go from our quantum numbers to the orbital where the electron is, or if you're given the information of the orbital where the electron is, you can find out the quantum numbers. Okay? So it works one way or the other. And hopefully by the end you have examples of both. So quantum numbers, we're going to have four different quantum numbers. Okay? Each one represents a specific thing. The first one is the one that I already told you. These energy levels here, N1, 2, and 3, and these are not the only ones that exist. You can go all the way up to N7. And you will see why. That first energy level, second energy level, third energy level, or way all the way up to 7, it's your principal quantum number, okay? Which we use the letter N to represent. So your principal quantum number represents the energy level, and it can go from N1 all the way to N7. Your principal quantum number it's given by the period in the periodic table. So your periods are going in this direction. So you have 7 periods in the periodic table, and your principal quantum number N can go from N1 all the way to N7, and you will see when you have to use N1, N2, N3, and so on. And we go all the way to maybe N5, no higher than that. The second quantum number is the angular quantum number, and we use the letter L to represent that one. That's a sub-level, and also you might see that word shells. instead of level, the word shell. So inside of your energy levels, we're going to have sub-levels, and those sub-levels are given by the value of this second quantum number. Now, what is very important about this angular quantum number is that they're telling you a specific type of orbital. We're going to go over 4 different types of orbitals, and each specific type of orbital is associated with a value of L. So that type of orbital will be determined by the number that you're getting for this quantum number right here. So how to get the value of L? This is what you need to know. You need to know the value of N, and depending on the value of N, you're going to have possible values for L. So the value of L, the second quantum number, it always starts at 0. And it will go from 0 all the way to n-1. So for example, if you're in the 4th energy level, N equals 4. So the values of L, it will start at 0 and it will go all the way to n-1. Since N is 4, n-1 is 3. So the value for L, you can have a value of 0, 1, 2, and 3 if N is 4. And it will always be like that, starting at 0 and going all the way to n-1. So to find out your angular quantum number, you have to know the value of N. The third quantum number is the magnetic quantum number. So this one here, it's going to give you different possible values, and depending on the amount of possible values that you can get for this magnetic quantum number, you can determine how many types of orbital of one kind you can have. So to get the values or possible values for this quantum number here, you need to know L, okay, which is the second quantum number. So to find out the second quantum number, you need the first one, and to find out the third one, you need the second one. So the possible values for M sub L is a range of values, okay? Same as your second quantum number L, you have a range. It goes from minus L all the way to plus L. So you need to know the value of L to find out the values of M sub L. So I have a table here that I'm going to use to put all of my possible values for my quantum numbers. Your principal quantum number, which is telling you the energy level, that's N. So I'm giving you the value of N. If N is 4, we're going to find out the values of L. And the values of L, they go from 0 all the way to n-1. So N is 4, n-1 will be 3. So the values of L will go from 0 all the way to 3. Then when N is 3, your principal quantum number, it's 3. That means that you are in the 3rd energy level. And for 3, the values of L goes from 0 all the way to 2, because n minus 1 in this case is going to be 2. When you are in the second energy level, n is 2, and then you're going to have values of L that are equal starting at 0 and not higher than 1, because that's your n minus 1. 2 minus 1 will give you 1. And finally, in the first energy level, you're going to have a value for n that is equal to 1, and your values of L is just one possible value starting at 0, and then n minus 1 in this case will be 0, so that's your only possible value. Now you can see here that in the fourth energy level, you have 1, 2, 3, 4 sublevels. In the third energy level, you have 1, 2, 3 sublevels. In the second one, you have 1 and 2, and in the first one, you have only one sublevel. Now, for each value of L, right, your second quantum number, you can find values for m sub L, the third quantum number. So m sub L goes from minus L all the way to plus L. When L is 0, there's no such thing as negative 0 or positive 0, it's just 0. So you have only one possibility for that. And you can go ahead and do the same thing wherever you have a value of 0, because it will be the same thing. When you have a value of L equal to 1, now the possible values for m sub L, they go from minus 1 all the way to plus 1. Okay, so your 0 is in between minus 1 and plus 1, which means that you have to list that one too. So L equals to 1, that will be 1 minus 1, 0, plus 1. So in this table, wherever you have a value of 1 for L, you can go ahead and write down minus 1, 0, and plus 1, because it will always give you the same. And then we are here where L is 2. I'm sorry. So if L is 2, the possible values from m sub L, they go from minus 2 all the way to plus 2. So minus 2, minus 1, 0, plus 1, plus 2. And you have 2 in the fourth and in the third one, so you can write it down. And we're missing just 1. When the value of L is 3, the possible values for m sub L are going to be minus 3, minus 2, 0, plus 1, plus 2, plus 3. Now, the magnetic quantum number is telling you how many orbitals of each type you have. Now, when you have a value of L that is a 0, that represents a specific type of orbital. When the value of L is 1, that's a different type of orbital, 2 a different type, and 3 in another type. Now, to determine how many of each one you have, you need to check out how many possible values for m sub L you have. When L is 0, you have only one possible value for m sub L, which means that for that type of orbital that you have when L is 0, you're going to have only one of them. Wherever you have 0, you can write down a 1. Now, when you have a value of L that is equal to 1, you can have 1, 2, 3 possible values for m sub L. Each possible value represents one orbital. So when L is 1, you have 3 possible values. That means that for that type of orbital, you're going to have 3 of them. And then When you have L equals to 2, that represents a specific type of orbital, and you have 1, 2, 3, 4, 5 possible values of m sub L, which means that for that specific type of orbital, you're going to have 5 of them. And then when L is 3, right there, you have 7 possible values for m sub L, which means that for the type of orbital that you have, when L is 3, you're going to have 7 of them. Now, I'm doing this when the energy level is 4 because this is repeating, you know, the other one, so you don't have to do it again. When you have 1, you're going to have 3. When you have L2, that's going to be 5. Okay? And then L1, that's going to be 3. Okay? So whatever you have, L equals 0, that's 1 orbital for that type. Whatever you have, L equal 1, that will be 3 orbitals of that type. It's here, and it's here. Whatever you have, L equals 2, you're going to have a specific type of orbital, and you're going to have 5 of that specific type. And then when you have L equals 3, that will be 7 of that specific type of orbital. So now I'm giving you the value of L, and these are your 4 possible values. Okay? We're not going over anything higher than 3. So your 4 possible values, 0, 1, 2, and 3, and this is the type of orbital that it's associated with each possible value. If L is 0, that's an s orbital, and whatever you have a value of L equal to 0, you have only 1 possible value for m sub L, which is 0, which means that you have only 1 s orbital. When you have a value of L that is equal to 1, you can have 3 possible values for m sub L. -1, 0, plus 1. So 3 possible values for m sub L means that you can have 3 orbitals. Of your p orbitals, it's 3. When L is 2, you can have 5 possible values for m sub L, which means that you're going to have 5 d orbitals. And then when the value of L is 3, the value of L equal to 3 represents an f orbital. If L is 3, you can have 7 possible values for m sub L, from -3 all the way to +3, which means that you have 7 f orbitals. This is how many orbitals you have of each type. In all of the energy levels where you have s orbitals, which is from the first one all the way to the 4th one, you will have 1 s orbital. Then in the first energy level, you don't have p orbitals, d orbitals, or f orbitals. In the first energy level, you have only s orbitals, which is what we're doing now right here. In your first energy level, n it's 1, the value for L, right, will be 0. From 0 all the way to n-1, 1 possible value for L. If L is 0, the type of orbital that you have is s orbital. And that's just 1 s orbital. Okay? So I'm going to represent my orbital here, just 1 orbital with 1 line. Okay? Now, in the second energy level, n is 2, and your possible values for L are going to be 0 and 1. Second energy level, 2 possible values, 0 and 1, which means that in this one you have s and p orbitals. Because whenever L is 0, that's an s orbital, and whenever L is 1, that's p orbitals. And when energy level is 2, you have 0 and 1 as your possible values for L. So your possible values of L are telling you the type of orbitals that you have. If it's an s orbital, that's just one orbital. If it's a p orbital, it's always 3 of them. Now moving to the third energy level. Now it's the third energy level, which means that you're going to have three sub-levels. And your 3 sub-levels are given by the value of L from 0 to n minus 1, which means that it's going to be 0, 1, and 2. 3 sub-levels, 3 values of L, 3 types of orbitals. 0, 1, and 2 is s, p, and d orbitals. If you have an s orbital, that's always 1. P orbitals, it's always 3. And then d orbitals, it's 5. And now we are in the last one that we're doing, the 4th energy level. 4th energy level means that you have 4 sub-levels. And the sub-levels are given by the second quantum number, the value of L. L goes from 0 all the way to n minus 1. So n is 4, and it will go from 0 to 3. So that's 0, 1, 2, and 3. A value for L equals to 0. It's an s orbital. 1 is p, 2 is d, and 3 is f. So you have all different types, 4 different types of orbitals in the 4th energy level. 1, whenever it's an s orbital, you have 1 of them. If it's a p orbital, it will be 3. D orbitals is 5, and then for your f orbitals, we have 7 of those. Now, the quantum numbers are defining the orbitals, and we are going to use those orbitals to put electrons. So the energy, it's increasing as you move away from the nucleus. So you can think about having the nucleus close to your first energy level, and then the energy is increasing as you move away from the nucleus of the atom. So we're going to follow three things to write down the electron configuration. The electron configuration is just putting the electrons in different energy levels, specifically in your orbitals. Yeah? So we're going to use the energy levels, the orbitals, to put electrons. So before we can do that, we're going to look at this right here. Okay? This is like steps to follow. Or things that you should remember when you're writing the electron configurations. The Pauli exclusion principle, no more than 2 electrons per orbital, and that's very important. Each electron is described by a set of 4 quantum numbers. You already have 3, we're missing the last one. So you cannot have 2 electrons with the same set of quantum numbers, because you are not going to have 2 identical electrons. So 4 quantum numbers, at least one of them has to be different for your electrons. So no more than 2 electrons per orbital, and you will see a couple of examples of that. Aufbau principle, it's how we're going to assign the electrons, always starting in the first energy level, and usually we go from an s orbital to p orbitals to d orbitals. S orbital, they have lower energy than p, they have lower energy than d. And then Hund's rule, you will see with an example. Okay, you can copy what it is, but not until you have an example you will be able to actually see what's happening in this one. So I am representing what I have in the table in a different way. What you have in this table, you see, 1 energy level 1 is orbital 1 line, 2 energy level 2 s and p orbitals 1 and 3 lines, The same thing that you have here, it's what I have down here. First energy level, you have one s orbital in there, and since it's in the first energy level, I'm writing the 1 right there. In the second energy level, you have s and p orbitals. For your s orbital is 1 of them. For your p orbitals, you have 3 of them. Then we move to the third energy level, an s orbital, 3 p orbitals, and then 5 d orbitals, and then in the fourth one, you have s, p, d, and s. So increasing energy as you go that way. And we're going to use this to write down the electron configuration for different elements. So I'm going to start with 1 electron. I'm not telling you element or anything. We're trying to put that electron in a specific place in the atom. So 1 electron, it means that you cannot have more than 2 electrons per orbital, but this is just 1 electron, so you don't have to worry about making any mistakes in here. Always from the lowest amount of energy and then moving up as you need to add more and more electrons. So for 1 electron, that only electron will be located right there in your 1s orbital. First orbital closest to the nucleus, that one is the one with the lowest amount of energy. So 1s, and then we use this notation right there. 1, because that one represents the electron that you're trying to write down the configuration for. Now, the other notation that we use is just writing it like this. Like I have it here, but it will be in a horizontal kind of way. So for this one, you have your first energy level, your s orbital, 1 electron, and we use this right here. It's like having half an arrow. Depending on the book or reference that you're using, you might have like an arrow pointing up or pointing down, depending on which electron you're adding. So this is 2 possible ways of having the electron configuration, depending on the number of electrons that you have. So that's the first one. If you have 2 electrons, in your Pauli exclusion principle, you have that you cannot have more than 2 electrons per orbital. So you can have 1 electron or 2, no more than 2. If you have 2 electrons, that's still good. You can put up to 2 electrons in that 1s orbital. So I'm going to have 1s, but now it's not 1, it will be 2 because you have 2 electrons. And then the other way of representing that electron configuration is like this. That's your 1s. Same thing that you have here. 1 electron is pointing up. 1 electron is pointing and down. Okay? And what that means is that your electrons, they have opposite spins. Okay? So they have opposite spins. 1 is pointing up, 1 is pointing down. And you will see what that means whenever we get to the 4th quantum number. Okay? So now let's do for 3 electrons. 3 electrons. Look, in each orbital you can put up to 2 electrons. So now you have 3 electrons, which means that you cannot have 3 electrons in that 1s orbital. You can have up to 2 electrons in there, and then the third one, you will have to find another place to put that one. And that place will be that 2s right there. So electron configuration for 3 electrons will look something like this. 2 electrons in here, and then the third one will go in a 2s orbital. So that's 2s, 2 electrons plus 1. That's a total of 3 electrons. So your other way of representing this is your 1s, your 2s, up, down for those 2, and always pointing up first. When you're writing your first electron that you're placing in your orbital, that one will go pointing up. and then whenever you're adding a second one, that one will go pointing down. For electrons, if you have to accommodate 4 electrons, you should use the first energy level first. In that one you can put 2, up to 2. After that one, you're moving to the second energy level, to the s orbital, s, then p, then this, in general. So for 4 electrons, that one will look like 1s2, 2s2, and this other notation, it will look up, and down. 4 electrons, 4 electrons. So I'm going to keep doing a couple of more examples. Now we have 5, 6, 7, all the way to 10. And you can keep looking at the diagram down here to write down your electron configurations. So the number of electrons is cumulative. You can look at the periodic table. You go from 1 electron, atomic number 1, to 2 electrons, then 3, then 4, then 5. So the number of electrons that you're using to write down your electron configuration, it actually comes from the element in the periodic table. When you're writing the electron configuration for 5 electrons, if it's a neutral atom, 5 electrons is what you have in your element number 5. 6 electrons is what you have in your element number 6, that will be carbon. And 7 you have nitrogen, and then 8 you have oxygen, and then 9 it's fluorine. And finally, right there with 10 electrons, you have neon. Which means that the first 4 electron configurations that we did, that's hydrogen right there, that's helium right here, that's lithium, and this one is beryllium. 1 through 4, and then we're doing 5 all the way to 10. So 5 electrons, 1s2, 2s2, that's 4, and you need a 5th electron. So 2 electrons in that one, maximum of 2 electrons in here, that's 4, and the 5th electron will go in a 2, energy level 2, in a p orbital. So that right there will be 2p1, 2, 4, and 5. So now you need to add a 6th electron, which means that you need to go from your P1 to P2, P3, P4, P5, and P6, adding just 1 electron. And it can go from 1 all the way to 6. You see how we have only 2, a maximum of 2 for your s orbital. But for your p orbitals, you can go from 1 all the way to 6, because every time you have p orbitals, you have 3 of them. And then you can have a maximum of 2 electrons per orbital. 2, 4, and 6 is the maximum number of electrons that you can put in your p orbitals, 2 per orbital. So your p, they can accommodate from 1 all the way to 6 electrons. There. So from 1 all the way to P6, and you can check 2, 4, and 6, that's 10. 2, 4, and 5, that's 9. 2, 4, and 4, that's 8. 2, 4, and 3, that's 7. 2, 4, and 2, that's 6. And then 5 in this one. Now, something that is going to be different, it's how you accommodate your electrons in the other notation. I was showing you this notation and then also with lines. And look how many lines I'm drawing here. One for the 1s, another one for the 2s, and then my 3 for the p's. So this represents my 1s, my 2s, and these ones are my 2p's. In your 1s, you have 2 electrons. So from this one, you can just do this one. And then in your 2s, you have 2 electrons. And then in your p's, you have only 1 electron. So I'm going to put that electron in the first one and pointing up. Whenever you are putting electrons single, just 1 electron, always pointing up. Now, for carbon, you still have the same lines. 1s orbital in the first energy level, and then 1s orbital in the second, and 3p orbitals in the second. So all of these ones are your 1s, all of these ones your 2s, and all of these ones your 2p's. For all of them, 1s and 2s is the same. 1s2, 2s2 for all of them. What is different between them is the number of electrons that you have in your p orbitals, so from 1 all the way to 6. So this is the part that is going to be different for all of them. Okay? This is the same, 1s2, 2s2, 2p1, and then for 6 electrons you have 2p2. And I'm going to refer to your Hund's rule right there, which I told you that you were going to see later. Orbitals of the same energy. Look, 2s has a higher energy than 1s. It's increasing going that way. But your 2p, you have 3 orbitals for your p orbitals, and they are aligned exactly in the same line, which means that they have exactly the same amount of energy. So when you have orbitals with the same amount of energy, you're going to put electrons single first until you have no more orbitals available, and then you can start pairing them. So for carbon here, you have 2 electrons in your p orbitals, and you have 3 p orbitals of the same energy available. So I'm going to put 1 and 2 electrons single first. You have plenty of room to accommodate up to 3 electrons, which is going to be your nitrogen here, without pairing them. So for nitrogen, you will have 1, 2, and 3. Then now when you get to oxygen, you have enough space to put 3 electrons on their own, 1, 2, and 3. But for oxygen, you have P4. It's a total of 4 electrons. So now the 4th electron, there's nothing else that you can do but to pair that electron with another one in one of your orbitals. So when you move to fluorine here, you're going to have 5 electrons in your p orbitals. So that will be 1, 2, and 3, 4, and 5. And then when you get to neon, you have 6 electrons in your p orbitals. That's 3, 4, 5, and 6. So this is an example for the Hund's rule. How do you apply it? If you have 3 orbitals that are available, you're going to put electrons in those orbitals single first, and then when you don't have more orbitals available to put electrons single first, then you're going to start pairing them. And something similar will happen with your d orbitals. For your d orbitals, you have 5 d orbitals. So you can put up to 5 single electrons first, and then after the 5th electrons, if you have more than 5, you need to start pairing them. So there's another way of writing down the electron configurations, okay? And it's using a short notation, and to do that, we're going to refer to the periodic table. So these are just steps that you can use to write down this electron configuration in this way. You're going to find whatever element you need to write down the electron configuration, you're going to find that one in the periodic table. And then you're going to look at the periodic table and identify the noble gas that is in the previous period, or that it contains a lower amount of electrons than the element that you're trying to get the electron configuration. You're going to put the noble gas, the symbol, in brackets, and then you're going to complete the remaining electrons using the periodic table. So before writing the short notation, let's write down the electron configuration for sodium. Okay? The whole thing. Sodium is 11 electrons. Okay? So you start again with your 1s. There's 2 electrons, 2s2, 2p6. That's the same that you have for neon, which is 10 electrons. So you have 10 electrons right there. Okay? So let's check our diagram right here, and we are in the 2p6, which is here. And after your 2p6, this is what you have, 3s. Okay? So you're moving from your 2p6 to the 3s, and in that one you need just 1 electron because you have 10 already, and this is 11. So that's it. Now, if you check this right here, it's the same electron configuration as neon, exactly the same. 1s2, 2s2, 2p6. So when you're writing the electron configuration using the short notation, this is what you do. You're going to find sodium here in the periodic table. And the noble gas that you have right before sodium is neon. Sodium with 11, neon with 10 electrons. So that noble gas you're going to put in brackets. That is giving you already 10 electrons. So to go from 10 to 11, you're just missing one electron. Now look what you're going to do. Right here you have your group 1. Group 2. Group 8. Sodium, it's in period 3, group 1. Okay? So right after neon, it goes a 3 because that's the period where sodium is. And with the periodic table, look, if you are in group 1, electron configuration is going to end in S1. In group 2, S2. In an s orbital, you can have up to 2 electrons, which means that with the elements in group 2, you're going to finish with the s orbitals. And then, if you check the second block, this part, right, in the periodic table, look, 1, 2, 3, 4, 5, and 6, exactly 6. Your p orbitals can accommodate from 1 to 6 electrons. So in this part of the periodic table, starting in p1, going to p6. So for sodium, which is the one that I'm trying to show you here, you have sodium right there, 11 electrons. The noble gas that you're using is the one that is in the previous period, which is neon right there. That's 10 electrons. So to go from 10 to 11, you're missing just 1 electron, and that 1 electron is in a 3s orbital, and that's S1 right there. So that will be 3s1. which is the same thing that you have here, neon and then 3s1, neon, 3s1. Let's write down the electron configuration for a short notation. Magnesium, which is 12, and let's do potassium, which is 19. Let's do those two. Magnesium is right here in your third period. So if you're looking at an element in the third period, you need a noble gas that is in the second period, which is going to be neon. So I'm going to write down the noble gas in brackets, that symbol, and then that will be followed by 3, which is your period number where magnesium is, and magnesium is in group 2, so that will be S2. Doing potassium, which is 19. Potassium is in the fourth period, which means that you need the noble gas that you have in the third period, which is going to be argon. Argon is already giving you 18 electrons, so you need an additional one. So argon, 18 electrons. And then after argon, what you need is 4, and group 1 will be S1. Now I'm going to do 1 on the other side for your P block in the periodic table. I'm going to do aluminum, and then I will assign you 2. So aluminum, it's right here in your periodic table. It's in period 3, which means that you need the noble gas that you have in period 2, and that will be neon again. And then after neon, right, that's giving you 10 electrons, and you need to go from 10 to 13. So after neon, you're passing through 3s2, and then you have 3p1. You cannot write down 3p1 because that's 10, 11 electrons. You're not showing your 13 electrons. To go from 10 neon to 13, 10 all the way to 13, you're passing through 3s2 and then 3p1. So you're going to do those two, okay? The short notation. So for practice, write down the long one and also use the periodic table to find out the short notation for those two.